So hi everyone. Today we're still talking about the zigzag product, and it will take us maybe half an hour to finish this part, and then we're going to start with SL equals L, which is like a big theorem in complexity, but it heavily based on the zigzag product. So let me just make sure that we're on the same page. So the zigzag product was one of three operations, if you remember, scoring tensor and zigzag, that we introduced in order to construct expanders, and it kind of played the role of reducing the degree, right? So, I mean, the spectral gap, as we proved, is deteriorating a little bit. The number of vertices actually goes slight up a little bit, but that doesn't really matter. But the good thing about it is that the degree that you get by zigzagging G and H has nothing to do with the degree of G, only H. So this allows us to reduce the degree. And the definition was as follows. I mean, in a high level, because I don't want to repeat everything. So the vertices were the vertices of the zigzag graph were like, so the zigzag of G and H were a pair of a vertex of G and a vertex of H. We thought of this as, you know, for every vertex of G we have a cloud. So this is not a vertex, just a cloud name. And at every cloud you have a vertex per vertex of H, or per degree of G, because it's the same thing. And the name of the vertex was U, I, so CTU neighborhood I. U is the vertex in G and I is the name of the vertex in H. And the way vertices like that were connected is as follows. So you're given two elements from the degree of the graph H. So if H has degree C, or I call it D1 here, you have like, you get a tuple of D1 elements. So A and B, I don't know where B is, it should be like here, but A and B. And what you do is, you know, you start at some vertex, ignoring the fact that you are at cloud I. At cloud U, you're just going to look at I as a vertex of H. You're going to take a step in H according to the first label that you got. You're going somewhere within the cloud to some other neighborhood. Then you take the unique neighbor of U, so the I prime neighbor of U. I prime is the vertex you reached by moving from I using A. So this moves you between the clouds, so that's an intercloud step. And then you use your second cloud, so your second label B, to move from whatever you got to another vertex of H. And, you know, the reason you got to J prime was because, you know, V is the I prime neighbor of U, but V consider U as the J prime neighbor. Remember that. So the end result is that using AB, so the AB edge neighbor of vertex UI is vertex VJ. Okay. So we did that already, talked a lot about it, and that's the main theorem we proved. That's the only non-trivial thing, the spectral expansion. So omega, you get, I mean, it's kind of, it's a good karma. You get one hit of omega G and two hits of omega H, because you do two steps of H and one step of G. But that's actually not tight. It's not like, you know, that's, you deserve better. So one thing you can prove, and I think I said it in a remark, and we will use it today, is that you actually get a better bound. It's not clear that it's better. You need to kind of substitute 1 minus omega to see. But gamma is 1 minus omega of everything, so that's gamma of the zigzag product graph, and that's of H and G. And that's actually what you get if you do the analysis slightly more carefully. And actually, that's what we did here, and I just kind of ignored things I could have not ignored, like that. Okay, there are two things I ignored, this and another one. If I wouldn't have done that, or in other words, if I would have done the analysis using gamma instead of omega, then you would get this bound, which again is like good karma, 2 gammas of H and 1 gamma of G. But, that's a better karma. Okay, we proved that, and that allowed us to start. Maybe I should just, okay, let's revisit that again. So using that, we gave an explicit construction, but we didn't say why it's weakly and so forth. An explicit construction of an infinite family of d-regular graphs for any d that you want, any constant d that you want. Right, and do you remember this? So the way to do that, we took so we are actually shooting for a graph which is d squared regular, you know? And to do that, it's easier like that. And to this end, we took a kind of a gadget graph H, which is D regular on D to the 4th vertices. If you think of this as constant, you can just find it brute force. If not, you can use problem 5 from the homework. It gives you something much better than that, and so forth. So it gives you omega, which is like 1 over D something. It's better than 1 over 8 for large enough D. So you take a small gadget graph H like that, and you iteratively define the graphs in the family as follows. So the first graph, the smallest one, is H squared. And then every other graph is obtained by squaring the previous graph, zigzagging with H. Right, and we said things, right? We said that, what's the sizes of the graph, number of vertices, size is number of vertices here. So H is of size, number of vertices is D to the 4th. Squaring doesn't change that, right? It adds edges above the vertices. So the first graph has size D to the 4th. And what about, what's the invariant that we're having, or how the graphs grow? Well, GT has some size, whatever it is, we'll call it the size of GT. Squaring doesn't change that. And zigzagging multiplied by the size of H or the degree of GT. So assuming that this zigzag is valid, and we need to make sure that the degree is the same as the size, the graph sizes increases by multiples of H all the time. H is of size D to the 4th, so eventually we get that the Tth graph in the family is of size D to the 4th, or D to the order of T. I don't really care about the 4. And we also said that the degree is, the degree of G1 is D squared, because the squaring a D regular graph is D squared regular graph. And the degree of the zigzag, when you do degree computation of zigzag, you can just ignore this part at all completely, because the zigzag takes the degree from the other graph. And the degree of G to T plus 1 is just the degree of H squared, because you get 2 steps from H. So it keeps the invariant is that the degree is D squared, the graph grows, and the only thing that we didn't do is the omega, I think, which is the interesting part. And why is this weakly explicit? It looks extremely explicit. I mean, I don't know. It's a really simple recipe to generate the graphs, but it's not explicit. Strongly explicit. So let's do that first of all. Let's start with the omega. Okay, so what I'm claiming is that omega is at most 1/2. Okay, I can do better, but omega in this construction, omega is at most 1/2. If you recall, the graphs for which omega is bounded away from 1, we call like expanders in general. But sometimes in some cases you want to shoot for the best trade-off you have with the degree. So if the graph is D squared regular, you want something like 1 over, up to constant, like 1 over D omega, like 1 over the square root of the degree. But let's just shoot for 1/2. You can do that here also, not 1 over square root of D, but 1 over the D quarter or something, we'll see. Oh, good. So here we don't even use tensoring, which if you recall, tensoring was the way to increase the graph size rapidly. And we are not doing that yet. And that's the reason for the weakly explicit. We will tensor afterwards. But let's see, what can you say about omega? It's actually a very simple calculation. Maybe I'll do it here so that you can see everything. I'll just erase these things. So we know, even by the weak bound that we have, that omega of the zigzag graph, in general, is at most, let me just continue. Omega of G to the T plus 1 is at most, we are taking a zigzag of 2 graphs. And if you recall, the omega is at most the omega of this plus twice the omega of that, right? That's the karma. So the omega of GT squared plus twice omega of H. That's how zigzag works. And the point is that, if you assume that omega of GT is at most 1/2, it's the invariant that you are trying to prove it holds, then this square you can just kind of move outside, because that's how squaring works. So if this is at most 1/2, this is at most 1/4, and the other one was choose 1/8 on purpose, so that this will be another 1/4, so you get 1/2. So if this is at most 1/2, then that's at most 1/2. That's how it. I mean, you see that we kind of. I mean, maybe it's getting better and better, and you can ignore that, but that's definitely true. So why is it weakly explicit? Can you see that? I mean, what's wrong with this? Why can I tell you who is my neighbor and polylog in time? Like, it's recursive. Good, very good. So it's recursive, and I mean there are a lot of recursion levels here. So let me say what I mean. So let me just copy that. So say I want to compute the neighbor. So I'm computing pi, right? The neighbor of a given vertex, right? The edge rotation map. And let's denote by t of t the running time it will take me to actually do that. T is the index of the graph in the family. So in order to compute, to access gt plus 1, we need to do these things, right? We have two calls to gt because gt squared. So we're given a and a b, and we need to run this twice. And it's time complexity, so we need to add this up rather than space. So we have like 2t minus 1, just because we have two calls for the previous recursion, and then we have then we have nothing. Then we have a zigzag with a graph which is of constant size. If I think of this as constant, so I can definitely write this as plus O of 1. There are some details, right? The zigzag, if you actually draw this, then you take a step in h, then you take a step in gt squared. So maybe I can write it like that: 2 steps in gt, and then you take another step in h. This is h, this is gt, this is gt, this is h. So this is the bulk of the time, really. These are kind of constant time steps. If you do it like properly. If not, it depends also on the graph size here. But the degree keeps the same, so it's actually constant all the time. It's like if you really care about it, it's like O of d of 1. So it depends on the degree. But even without that, even if this was like a 1, just a 1, you see that this comes to like 2 to the t also. And okay, but what's the graph size? I mean, everything is proportional to the graph size. We said something d to the 40 or something. It doesn't really matter if it's a 4, just it's a d to the t. And you see that, tt is something like, so let's call it nt, n sub t, like something like this. You take the d outside, maybe a 4, there is a 4 somewhere. Doesn't really matter. So the running time, if this constant, is polynomial in the graph size, right? Because the graph size increases exponentially, but also the running time. The running time increases exponentially slowly a little bit, but more slowly. D is maybe 64, so you get like n to the 1 over 6, but it's still polynomial time. And that's not strongly explicit. That's weakly explicit.
Something doesn't add up here. I mean, the running time can be lower than the space.
Yes.
So, like, get space.
Space or
like the size of the graph.
Yes.
Is something we can't possibly make less.
Right.
Less like instructions.
Right. No. So what I'm computing here is right. For a given vertex, I'm telling you I. Tell me its neighbor. Right. So it's locally accessing the graph. You're right. It's not linear. It's sublinear. So something interesting is happening here. So I can tell you the neighbor, the ith neighbor of v in time which is less than the time required to writing the graph down. But it's not polynomial in the input length, which is v and I, because v and I are of logarithmic in the graph size, and here I'm running time which is polynomially small, like maybe square root of n in the graph size. So it's non-trivial. It's not explicit. It's explicit. It's actually stronger than weakly explicit in a sense, but it's not strongly explicit. Mid explicit regime. But it's not enough. Usually you care about strong explicit because the graph size is exponential in your input parameters. And the reason this holds is because we had a lot of recursion. I mean, we did well in every recursive level, but we had many recursive levels because the graphs increased slowly. Right? That's the reason. So the way to bypass that is to tensor. So here is a better construction. It has some downsides, which you will fix in the homework. It's really easy, but if you understand this. So it's exactly as what, I mean, before we just had this replaced with a GT. Right? We took a graph. Now it's going to be on D to the 8 rather than D to the 4 vertices. We kind of have to do that, you'll see. But besides that, we do square and zigzag, but we also tensor to increase the graph size rapidly so that number of recursive levels won't be too large. So let's analyze that. But that's what's going on here. Okay, let's start with the degree. Degree is always easy. So H is again D regular, but with D to the 8 vertices. What's the degree of G1? H is D regular. D squared, right? Like this, squaring a graph, squaring the degree. Right? Squares the degree. So the degree of G1 is D squared, but I don't even write G1 because we know that what I'm going to say is the degree of every graph is D squared, because the degree of this graph, it has nothing to do with what's written here. So we already computed it. It only depends on that part. And the degree of H is D, so the degree of GT plus 1 is D squared. Completely decouples. Zigzag completely decouples the degree from that side of the zigzag. It's really cool.
Yeah. I wonder, because of the tensor, would be able to do it parallel this zigzag?
Yeah, but then there's a square and a zigzag. I don't know.
Because like if you do the zigzag on the GT, and then you do an H, and then you do the GT again, and then
maybe you can make it parallel. Yeah, could be.
Yeah, you have to make parallel as well. Like if you look only on the string, wouldn't.
Ah, right. But you mean okay? It would be just log n. That now it would be like log n maybe. That's right. But you're right. It's not the recursive level. It's not that high. It's just logarithmic. Right. Here it's going to be double logarithmic. So the degree is D squared. The graph sizes. So GT. I'll do G1. G1. What's the size of G1? I'll do G1. So it's the size of H. So I know that it's D to the 8. Right? G1 has size which is the size of this thing, but square doesn't increase the size, so just H. And the size of GT plus 1, well, let's see. So the size of GT, we now square it, unlike before. That's the feature now. So GT plus 1 is, okay. So you have a GT squared because of that. Not because of the square, actually, because of that. And when the square doesn't affect anything in terms of size, and when the zigzag, boost it even further a little bit. I don't really mind. I'm fine with the square, but times the size of H. But even before we do that, we actually want, I don't know if before, but we also want to make sure that we can apply the zigzag. I forgot to do that. So we needed the degree of this graph will be the size of that graph. The size of H is 8 D squared, D to the 8. So let's make sure that the size of the degree here is D to the 8. So what's the degree of GT? It's D squared. It keeps getting D squared all the time. When you tensor, what happens to the degree? Square, so D to the 4th. And when you square, it's D to the 8th. So everything's fine. So we can apply the zigzag. And we see the GT, if you just do the calculation, it's like D to the 8 to the T. Because you just repeat doing that. Every time you just square, and maybe D to the, sorry, D to the, it's definitely 2 to the, okay, let's do one more. GT minus 1 times D to the 8 square. Yeah, I was right, okay. So this is like GT minus 1, 2 squared, D to the square 2 plus 1. So if you just, it doesn't matter, I'm just making sure. So this is roughly the graph size initially, so D to the 8 times 2 to the T. So that's something like that. It wasn't D to the 8 to the T, it was D to the 2 to the T essentially. I got confused a little bit. But the important thing is that it increases double exponentially fast. Right? D is constant, so double exponentially fast. So this means that after, if you want a graph of size n, after log n iterations, actually a bit less because D is maybe slightly larger than 2, but depending on the basis that you put here. But after log n iterations, we get a graph, maybe it's not of size n, but at least n. Of size at least n. Right? It's between n and n squared, more or less.
So it's for a large polynomial, but for a number, we can choose h so that we can make the replace the GT tensor with something which brings us to something which is close to log power.
Right, you can stop at some point and get closer to it. Right, that's actually one of the. So that's why I call it scarce, because you don't have many graphs. Like the family is kind of getting scarcer and scarcer between n and squared, rather than between n and 2n or n and plus 1. And that's one way to fix it. There is another way, which I'll show. I'll show, and you will do it in the homework, but it's easy. But I say we were fine with that. The graph increases rapidly, which in a second will help the running time. Otherwise, we don't mind that really too much. But the degree is great. It's squared all the time. But what about omega? So I claim I don't have to do anything. But why?
Squaring doesn't change the omega, right?
Squaring does. It helps. It reduces it. But the first thing you said, tensoring doesn't change anything, right? About the omega? It's the same as before, exactly. I can remove that. That was before the omega analysis that we did before, and tensoring doesn't change. So good. So we chose the examples that make the least local changes, right? I could have started something else. Good. And so what about the running time? Actually, here I don't have to do anything as well, almost. If we look at the running time analysis from before, now I only have to replace these two by a slightly larger number. How many GT calls do you have here? Like if you open it up. Here it was 2. Now it's 4, right? Because GT tensor GT, just you can do it in parallel, but time-wise, if you're just considering time, it's like 2 time steps, and then you square. So it's actually 4 time steps, 4 calls to GT, to the pi of GT. And that's it. So actually you get the same recursion, but you're only shooting for t, which is log n other than n. Because, so let me just do it here so that we can see the differences. So now t of t is at most 4. 4 doesn't. And it's an OD of 1 because it's zigzagging with h. And the point here now is that the size of GT is roughly, so let me just even be ignoring the d. It's like 2 to the 2 to the t, unlike 2 to the t from before. Right? So the t that the number of iterations we need to do that is roughly like log n, because we want to make this roughly like n. And the recursion of t, solves again to something like 2, maybe actually 4 to the t, but that's fine. That's like log n squared, right? Because 4 to the log n, even it's actually smaller than log n, but anyhow, log n is like log n squared. You comfortable with this log play games?
Is it 2 to the 2 to the t, or is it like
even more, right? It's like d to the 2 to the t times 8 or something. But it's definitely at least 2 to the 2 to the t, and it doesn't really help us that it's a little bit more. It's a little bit more because also the zigzag increases the size a little bit. So I'm ignoring that, and so you see, so you have less recursive calls. You do a little bit more per recursive step, but that's fine. It's cool, right? I don't know. Now the problem is this, as I said, is that you don't get, if you want a graph size n, you might get a graph size n squared or something, because you need the fourth t that goes over your n.
just the next step either way, like you got to about the size of, then you stop tensoring.
Yeah, you can. Actually, you can stop at below like a square root n or something. I don't know. No, it doesn't work. Right, because square root of n, then you have like square root of n to go. It's the same thing. Right. It's a good idea, but actually there is the fix is really disappointing. So what you do is replace, so the same thing as before, but instead of t, you have like t over 2, and just if you want to be pedantic, so it's uppers and lower, but it's t over 2, and that's it. And in the homework, you will try to understand why. So this increases rapidly, maybe slightly less rapidly as before, but it doesn't really matter, because it like instead of squaring, it's squaring 1/4 of what you get, because there is a half there. It doesn't really matter. And so it keeps scoring a lot, and you need to to understand it doesn't. It's not hard. Why this actually gives you a quite dense family, quite a dense.
What did it respond?
Okay. So currently, what you have is you have an n that you want to have a graph of size n that's expander whatever, and what we did is constructed for particular graph sizes expanders. So what will happen really is that you take the first one that's larger than your graph. You just have to walk around the fact that it's larger. You can't just take half of it. I mean, you need to work with the larger graph somehow. It's annoying. There are ways to increase the size without hurting omega, but never mind that. But if you had a graph of every size, you would be happy. If you had a graph of every between any n and 2n, you would be happy as well, because that would be at most twice the size graph that you wanted. But
it's always square.
Right, it's always square. So right, exactly. That's what I mean. The scars. We don't know how to construct graph of every size, by the way. It's not like we don't know how to do that, but it's not that construction.
Switch edges up.
You just open like a new course. But randomly, I mean, right. The one thing we don't have in this course is randomly. By the way, taking a random graph works also with high probability.
Take a small expander.
Take a small expander, what?
To do something random.
Expander.
Like, you need a little bit of confidence. When you suck it up, then you use it other times. So, like,
but then, if you use it again, there will be dependencies between the graph and what you do. So sometimes you can do that, but when you do that, it's like a good paper. It's like when you work against dependencies, it's like yes.
Here you can reduce the number of recursions if you express the seal one by the flow one.
No, because these are different neighbors. Like you take two different neighbors, A and B. So when you do tensoring, if you have the same graph, it doesn't help you, right? Because you need an A if neighbor here and a B if neighbor there. But maybe you can, because there are not so many A's and B's, maybe they will repeat things. But I don't know. Yeah. But that's good. That's good enough. Okay, just another homework problem that you have. These are easy homework problems. I mean, they're really easy. I can just write it here, the solution. It was written here. Removed it so that you will have interesting homework questions. So if you, so it relates to what I said with the 1/2. The 1/2 was just to exemplify things, but you can actually get 1 over d to the 1/4. So you can get a deregular graph using those techniques, and omega will be 1 over d to the 1/4. So remember the how do you, beauty queen of expanders that you said something. So this is 1. You don't want omega to be here. There's also minus omega. Everything that's bounded away from 1, you're happy with, but you can get actually all the way down to 2 square root of d minus 1 over d. That's the omega of Ramanujan graphs. That's the best you can do. Asymptotically, you can go slightly below when the graphs are small, but asymptotically. And so that's roughly like 1 over, maybe 2, I don't care, over square root of d. And this construction will get you here, 1 over d to the 1/4. Which is good, it's great, but it's not optimal. And actually you can tweak it, but not trivially, to get something that's even better, but still not 1 over square root of d. It's like the unread section 6 of the paper. No one reads it. But there is another section there that says, actually, we can do slightly better. But never mind that. Okay, questions about these things? So good. That's like a famous construction by RVW. It's Reingold, which will appear in a second also. Vadan, kind of the gods of pseudonymous, and Wigderson.
Talking about the Big Bang.
Right. So they introduced this thing, the zigzag product. It's the same. All of these are in the same paper. I don't present it from the paper. But I actually follow the presentation of Vadan's survey as a survey, a very nice survey that I'm linking from our website, and it's more or less what's written down. Questions about that? Good. Right. So actually, it's kind of funny. He died like way before. Right. So actually, the first construction, I think the LPS construction, they used, or maybe related to that, they used results related to Ramanujan's conjecture, and they call these graphs Ramanujan graphs. Every graph which achieves this optimal bound Ramanujan, which is not fair because there are other graphs that may achieve the same bound and they are not Ramanujan. It's like calling. It's like there is a bound, an inherent bound on what omega you can get. Yeah, but the name is like, I have some issues with it because the way they constructed this graph is related to Ramanujan conjecture, but there are other ways of constructing these graphs. No, he died before. Right. Yeah, he might have lived until that age, but he didn't. If he wouldn't go to England, it'd be fine. But when I said that at some point, I said that at NYU at some talk, and then someone told me, you call in Hebrew, you use the word Ben Adam. So Adam was like the first instance of a human being. So the graph Ramanujan is the first instance of a Ramanujan graph. So everyone is, so these are all graphs are Ben Ramanujans or something, Ramanujan sons. So that's fine, I guess. Right. There are other constructions, very interesting. I won't have time to cover them. There is one by Amnon Tashma, which builds on these ideas, but takes it further and actually get almost to like 1 over square root of d. And there's one by Bilu and Lineal, which behaves very differently. And there's one by, which we'll see next semester by MSS, Marcus Pillman Mastava. Gal will tutor the course and I'll teach it. And so forth. And there are a couple of other constructions. But let's stick with this construction, and we will see. Someone asked, why do we need a construction that's worse than what we had? It's actually more complicated in a sense, but it's less complicated in other senses. But why do we need that? So the point is that the techniques are interesting, they're useful, rather than the construction itself, rather than only the construction itself. So with that, let's move to SL equals L.